Hello, I am Besat Farhang, a PhD candidate of Mechanical Engineering at University of Texas at Arlington. In this recording, I'm going to briefly present the study conducted for Innovation Day project entitled Investigation on the Properties of Reinforced Incandescent Structures Fabricated Using Laser Powder Bed Fusion. Incandescent, a nickel-chromium-based superalloy, is widely used in various industries. Over the years, additive manufacturing techniques have been developed for the fabrication of incandescent alloy and other materials. Laser powder bed fusion, one of the additive manufacturing techniques, has the ability to fabricate highly dense parts by melting a layer of metal powder over and over as designed using various CAD tools. The properties of LP laser powder bed fused incandescent has been widely studied and improved by varying the process parameters such as laser power, scanning speed, hatch space, and layer thickness. In this study, a novel approach has been used to have two different process parameters and therefore leading to two different properties in a single part, making it a composite structure. In this case, four different rod geometries, including plane rods, helical rods, arc rods, and square rods, were designed, and an EOS M290 metal 3D printer was used for fabrication of the samples. The microstructure analysis of the parts was carried out using a Hitachi variable pressure SEM, and to perform microstructure characterization, the samples were grinded and polished using an allied mechanical polisher. Then the samples were etched before performing microstructure analysis, and the Vickers hardness of the samples was determined with the help of a local micro hardness tester under an applied load of 500 gram force. The composition of the as-obtained powder was determined using energy dispersive X-ray spectroscopy or EDS analysis as shown in figure 2. The analysis of the SEM micrograph of the fresh powder revealed the average powder particle size to be around 12 microns. Microstructure analysis of the as-built samples was conducted in order to study the cohesive behavior between the main sample and reinforced rod. Based on the analysis of the results, the plain rod sample had the least amount of surface porosity of 2.6% among all the samples. And this observation can be expected as the plain sample was fabricated homogeneously without having interface with any strengthening segment. The samples fabricated with helical and arc rods had a surface porosity of 2.8 and 3.2% respectively. The similar level of surface porosity observed for these samples can be attributed to the similar cross-section of their interface with the main section. Moreover, it is clear that the sample fabricated with the square rod had the highest porosity level, which can be attributed to the higher stress concentration arising from the sharp angles exist in the geometry of the square rods. According to the hardness results, the sample fabricated with plain rods resulted in higher Vickers at the interface. The samples fabricated with helical rods and arc rods had average Vickers hardness values. However, the sample fabricated with the square rod yielded a lowest hardness value. This can be attributed to the highest level of the surface porosity was found for this sample. Overall, in this study, cubic samples with reinforced rods of different geometries and process parameters were fabricated. It was found that the plain rod reinforcements had lower level of surface porosity compared to the other samples. The square rods, however, had a high percentage of surface porosity due to the sharp edges. The Vickers hardness analysis of the samples revealed that the plain rod sample had the highest hardness value, and the samples fabricated with the square rod resulted in the lowest Vickers hardness value. Thank you for your attention.